Ventilation is the movement of air between the atmosphere and the lungs, and air follows a pretty simple rule. It moves from areas of high to low pressure. So let's look at the different compartments of the lung to see where these pressure gradients might exist. So looking at this figure here, this is a cartoon drawing of a lung, and in the center part here is the alveolar space, so we will write that down as P sub alveolar, representing the pressure in the alveolar space. And then that alveolar space has two membranes around it. It has the membrane made up by the type 1 and type 2 alveolar cells, but outside of that is the pleural membrane. And the space enclosed by the pleural membrane and the cells making up the alveoli is called the intrapleural space. So inside here is the intrapleural space. And this has a pressure associated with it as well. And the pressure inside here we can call P sub IP for intrapleural space. The intrapleural space is lubricated with fluids that are secreted by these membranes. So you can think of these two, and this space is actually much, much smaller than what's drawn here. And in fact, these membranes are almost touching each other with a very thin layer of fluid in between them. So a couple of rules about the pressure differences between the alveolar space and the intrapleural space is that the intrapleural pressure is always lower than the alveolar pressure. And another pressure relationship that's always true is the intrapleural pressure is always lower than the atmospheric pressure, which we did not label on our diagram yet. So outside of the lung is where the atmosphere is, and of course this is where we can label our atmospheric pressure. And these two pressure relationships help to keep the lungs expanded. So this membrane is sort of pulled against this pleural membrane so that the alveoli don't collapse on top of themselves. Of course, if that pressure difference is ever lost and those pressures become equalized, that's when we have a situation where the lungs collapse, and we call that a pneumothorax. And of course, in that situation, our intrapleural pressure equals our alveolar pressure, which is then equal to our atmospheric pressure. And the alveoli collapse and stick together. And then don't perform gas exchange. So that's a bad situation to happen. That will heal over time, but it does take a fair amount of time for that to heal. So 2 punctured lungs would be a pretty bad thing to happen. So to understand how lungs are ventilated then, we have to look at the pressure differences between the alveoli and the atmosphere. So I'm going to draw on this graph that shows pressure in millimeters of mercury on the y-axis as a function of time on the x-axis. I'm going to show three different pressures on here. The first one is the atmospheric pressure. So we're only looking at this over a breath or so, so the atmospheric pressure will basically stay the same. So we show a straight line for atmospheric pressure. And then I'm going to draw another line showing the alveolar pressure. And this one's in blue. And this one is changing. So blue is P alveolar. And let me just do, we won't really talk about it much, but we'll put it on here for completeness. And that's the intrapleural pressure. And it kind of tracks the alveolar pressure. So put that one right there in pink. Okay, so notice that sometimes the alveolar pressure is higher than the atmospheric pressure, and sometimes it's lower than the atmospheric pressure. So in the case where the alveolar pressure is higher than the atmospheric pressure, remember that air flows from areas of high to low pressure. That means it's going to flow from the higher pressure area of the alveoli towards the lower pressure area of the atmosphere, or out. So we would say that air flows out of the lungs, and we call this expiration. Or exhalation, same thing. Exhalation. And in this situation, our alveolar pressure, if we want to write it in terms of pressure relationships, is greater than our atmospheric pressure. Notice that the intrapleural pressure is still lower than both the alveolar or the atmospheric pressure. So intrapleural pressure is less than atmospheric pressure, and intrapleural pressure is less than the alveolar pressure. So how do we create this change in pressure? Well, in order to make the pressure higher in the alveolar space, we have to take that volume of gas and squeeze it into a smaller space. So in this situation, the volume of the thoracic cavity is going to decrease. And this causes the alveolar pressure to increase. And how do we do that? We use skeletal muscles. So the diaphragm relaxes and it moves upwards. And so it ends up looking like that. It's a relaxed diaphragm. And the abdominals and internal intercostal muscles can contract during more vigorous breathing as well to help further make the volume of that thoracic cavity smaller. Abdominals and internal intercostals. When you're sitting breathing quietly, though, you're mainly using your diaphragm. So how about for air to flow in? Well, the case where air is flowing in, again, we have to have lower pressure inside the alveolar space than outside for air to follow its pressure gradient and move from outside to inside. And so here we have air flows in because we have higher pressure in the atmosphere and lower pressure in the alveolar space. And we call this inhalation or inspiration. And in this situation, our pressure relationship is that our intrapleural is less than our alveolar, is less than the atmospheric pressure. And for this to happen, the volume of the thoracic cavity has to increase for that alveolar pressure to decrease. And again, we use skeletal muscles, so the diaphragm in this case contracts. And it moves down and it flattens. That says flattens. Here is a contracted diaphragm. Again, the ribs can, or the intercostal muscles rather, can also be involved. The external intercostals pull the rib cage outwards and upwards. And that will, during more vigorous breathing, those external intercostals and also the scalenes as well can pull that rib cage outwards, increase the volume of the thoracic cavity, and of course you have the same amount of gas in a bigger space, and of course the pressure will go down and air will flow from outside into the lungs. So we just simply change the pressure inside the alveolar space by squeezing the air into a smaller space to increase the pressure, by contracting abdominals and internal intercostals, relaxing the diaphragm, air flows out, and then as the diaphragm contracts and the external intercostals contract, then the air is able to flow in as the volume in the thoracic cavity increases and the pressure goes down. So in this diagram you can see that the diaphragm is relaxed, so the air flows out as the alveolar space is smaller and the pressure is higher in the alveoli. The diaphragm contracts, and now you can see that the alveolar space has now increased from what it was previously. So the pressure goes down and air flows in. The diaphragm relaxes and air flows out. The diaphragm contracts, air flows in. Diaphragm relaxes and air flows out again. Now recall that we talked about in an earlier video how the alveoli shown right here, these yellow structures are the alveoli, and you can see they've got elastic fibers around them. That elastic recoil is important for exhalation in addition to the change in pressure we just talked about. But notice also that the pulmonary capillaries shown right here are in very close association with these alveoli, which allows for easy diffusion of gases. It results in a much smaller diffusional distance when those membranes are fused together. And this makes it really easy, this close physical proximity of the alveolar air and the blood. It allows for the tight matching of ventilation and alveolar blood flow. And this is to maximize oxygen diffusion into the blood and also to regulate plasma pH, which is strongly influenced by the amount of CO2 in the blood. And so when you're sitting at rest, you're not using all of your pulmonary capacity, just like when you're sitting at rest, you're not using all of your possible cardiac output. And you could overventilate your lungs and lose too much CO2, and as we'll see later, this is a fairly big problem. You can't really over-oxygenate your blood, but you certainly have to regulate the degree to which you ventilate in order to not lose too much CO2 from your blood. And so the alveoli that are not really being used because you don't need them, so are poorly ventilated, blood is actually diverted away from those alveoli. So you only send blood to well-ventilated alveoli in order to not overventilate and not lose too much CO2 from your blood. So let's look at an example of how this works. So in this cartoon here, we have two alveoli right here, and here are the pulmonary arterioles which are delivering blood to them. And notice that the diameter of the bronchioles is equal and the diameter of these pulmonary arterioles is equal. So then we have a situation where maybe this person was moving around and now they're just sitting quietly and not doing anything. So they are not ventilating all of their alveoli because they don't need to. So notice here that this bronchiole is narrowed and less ventilation is happening in this alveolus. So as a consequence, the partial pressure or concentration of carbon dioxide goes up, and the partial pressure, or we can think of that as the concentration of oxygen, starts to go down. So the gas composition in this poorly vented alveolus changes compared to the well-ventilated alveolus. So the next thing that will happen then in response to that is this pulmonary arteriole right here will constrict in response to the decreased partial pressure of oxygen in that alveolar space. And that means that blood is diverted away from this poorly ventilated alveolus and it's sent to the well-ventilated alveolus, so where there's lots of oxygen to pick up. It doesn't make any sense to send blood to poorly ventilated alveoli because if the partial pressure of oxygen is low enough in that alveolar space, you could potentially lose oxygen from the blood into the alveoli because oxygen moves by simple diffusion and follows its concentration gradients. Make sure to take a look at the notes and read about how oxygen is the primary determinant of the state of contraction of pulmonary arterioles, and on a minute-to-minute basis, carbon dioxide is the most important determinant of the state of contraction of the bronchioles. So we have to keep up with factors that affect the state of contraction of airway smooth muscle, pulmonary arterioles, and systemic arterioles.